Um, I want to welcome us again to this second session. We shall quickly, let me quickly share my screen. Let me share the screen so that we'll start. All right, are you seeing the screen?
No.
Let me see. Like, is my Chem3D showing?
You can see it now. I can see.
Are you seeing the Chem3D? Please,
Yes.
okay. Please always mute your mic if you are not using it. Just mute your mic. If you're not using the mic, just mute it. So we are going to look at the first series transition method. The first series. So we look at the first series transition methods and we'll model as much as possible. We'll model as much as possible. Let's start with which of these now should I use? Okay, let me use okay, let me model met for me. Okay, what we'll do here is that I'm going to model each of these compounds that I have here, each of them with zinc. I will model with zinc, and I will model with zinc and iron. I will model with zinc and iron just to show you. So each of them that is here with zinc and iron. So let me start with bromohexene. So if I want to model this, please, I will need my Chem3D. So let me open my Chem3D. Now, if I went to open another thing. Chem3D. So if I want to model it, I will follow the same process that I have already explained, which is copying the structure that you have built to Chem3D, optimize the energy and the geometry, then do your normal saving this and that, all those stuffs. So that is just what we'll do. And then we can get their structural properties. We can get their structural properties as well, because these structural properties will help broaden our understanding about those about the complex forms. So let me start with this man. This is bromohexene. I will copy it to this place. So this is a new worksheet. So this is my structure. This is my structure, the bromohexene, and I want to use zinc and iron, and I'm working with a coordination number of 4. I want to work with 4. Now you will see that this compound has only one is monodentate. It is monodentate, so that means I will need 4 of this. I will need 4 of this to bind with my zinc. So what I will just do is I have to align it up to 4. I will copy and paste again. I will pick one up. If I pick one up, okay, let me reduce the size. I will reduce the size so that it will enable me. So I want to form a zinc nanoparticle of this man, and I'm using zinc as a coordination number of 4, and I have identified that this compound is monodentate. We have passed that stage. It means I will need 4 of these to bind to my zinc. So I will just copy up to 4 of it. I will take up 4 of it. So I will take one up. I will take another one up. I will turn it to be like this so that it will be very easier for me to form the bond. I will make it like I just made it opposite. I will bring it closer. Then I will copy another one to this part. To this part. Maybe I can also rotate it to be like this. And probably take it closer. I will also copy another one to this part. I will rotate it so that I will rotate it to be like this, so I can easily identify. You know, our target here is the nitro group. So what I will now do is I will take up my zinc. I will come to this middle and place my zinc here. I will just type Zn for zinc. Having typed Zn for zinc, I will take the solid bond. I will start joining my nitrogen to the zinc. Join this one to this point. Join this one to this point. Okay. I will draw this to this point. Then I will draw this to this point. So at this point in time, I've been able to achieve the complex. So this is the complex, and this complex now I can call it if you want to give it a name, all these they are diaqua, tetra, I can call it zinc 2 tetra bromhexene. I can call it zinc 2 tetra bromhexene, but the name is not important to us. What we know is that is a zinc 2 metal complex of bromhexene. So having formed this, the next thing I will do is to optimize it. So I will copy it. You can still get the structural properties if you want. You can still from here get their chemical properties of that complex. But if this place may not generate, then we'll look at. I will show you another. I will show you a most preferable place to get their properties. So you see that we are unable to generate the properties from here. This place could not generate their properties. We can only have the analysis window. So the formula, look at the formula of the compound: C56, H76, bromine 8, N8, Zn. So it has already noted the formula with the exact mass. Now don't be carried away by this exact mass, though the mass might be high, but it has been made nano. Then the molar weight and so on. But then let me optimize it. I will copy it. I will copy, go to my Chem3D. I will paste in my Chem3D. So once I paste it here, you are seeing this screen. We already know that this screen is my 2D, while here is my 3D. So you see how clustered the 3D is. I will go to calculation. We know this part, and minimize the energy. So I will minimize the energy of the complex formed. So the bond, because the bond we are too clustered, so it's trying to separate, it's trying to align the geometry, it's trying to make the complex uniform. So that is because this stage is inevitable. This stage is very, very inevitable, unless you just want to use your 2D, but we don't work with the 2D. So it may take time, it may take a little bit time, but it's minimizing the energy, and when that is done, we will save it. But while that is going, I want to teach you something. Why that is going, most importantly, is the SMILE code. You can copy the SMILE code of this structure by come to copy as, take up the SMILE code and paste. So this is the SMILE code of our complex. Now if you are doing if you want to know the properties of this complex with this SMILE code, I can now go to any database at all, but not all database can understand this SMILE code. But let me take you to one of them that can understand the SMILE code. Let's open, let's look at Swiss admin. Let's see Swiss admin. So I will paste that SMILE code in my Swiss admin, so that I will get the properties of my complex. Although I will explain more of this Swiss admin by next week, because by next week we'll be entering chemoinformatics. We'll be entering chemoinformatics by next week. That will be throughout the first month. So let me paste. I just paste the SMILE code and I click on run. So you will see that this database can actually understand what we have modeled. So look at what we modeled. So Swiss admin is actually showing you the same structure you have modeled. So this is the structure we actually modeled. So Swiss admin can predict the structure for us. Then you can get some properties associated with that your structure. I don't know if you are following me. Hello?
We are here.
Okay. Because a complex in a graveyard that they talk. Everywhere just stay quiet. Well, it's not my sharp. If na physical class now, response for the choke everywhere. So this Swiss admin was able to understand my structure. But look at what will happen if I take it to PubChem. PubChem cannot interpret what I have drawn, because PubChem is not working by algorithm. PubChem works by what you have deposited inside. If I paste, so each time you are working with metal complexes and you want to get relevant information about the metal complexes, just get the SMILE code and come to your Swiss admin. You will get all the properties. Here is the macrokinetics. Okay, let me start from this place. This place is giving you the physical chemical properties of your metal complex, the lipophilicity of the metal complex. Then we can get the water solubility of the metal complex. From here, you can get the pharmacokinetics of the metal complex. you will get informations on the draw likeness, the draw likeness of the metal complex. So you see that if I'm to use this as a drug, it actually violated Lipinski's rule, Gross rule, Weber rule, but it will be more effective. Though I cannot tell if it's effective or not until we test the activity. Yes, until we test the activity to know if it's effective or not. So that is, I just want to show you this, that with your smile code you can get the properties of that your structure. So if you see this pop came now, if I put the smile code on this pop came, it will not read anything. Let me paste the smile code. It will tell you no match. Let's see what will be the response. See, 0 result found. So don't use PubChem when you want to get informations concerning your meta complex. You can use SwissAdMed. By next week we shall be dealing more on this databases under chemoinformatics. So let's come back to our 3D. It's still the energy is not yet done. It's still minimizing. So it's still minimizing. Why that is going, let's create another complex. Let me create another complex. Let me use metformin. Metformin is an anti-diabetic drug. So let me use metformin. So I paste my metformin here. Metformin, when we identify metformin, it was actually about 4, but for my experience I'm going to use these 2. I'm going to use only these 2. So I will take metformin as a bidentate ligand. I will not use all of them. I will use only these 2. It just by the time yes, is it a question? Okay, so I will use, like I said, I will use only these 2. And forming the complex. So this time around, let me create a complex with iron. Let me use iron for this complex. So that means I have to duplicate. Let me use iron. Okay, let me work with 6. Let me work with 6 for iron. So let me say iron 6. So or better, let me see work with the 4. So I will duplicate it. I will take another one up. Then what I will do is to rotate the one that is up, because I have already identified the bonds that I'm going to use. So I will just rotate it like this. Then I will shift it closer. Let it be like this. So the next thing I will do is to pick up my iron. I will pick up my iron. I will type Fe. Then I will take my bonds. One bond here. So you notice that the hydrogens are going out, because the bond must be balanced. So what I just did now is I have modded a nanoparticle of metformin with iron 2 complex. So let me check if this one is done. Okay, this is not yet done. It's not yet done. We just have to wait until it's over. It's actually a heavy molecule, but I think I will quit it. I cannot wait for it because I am on a training class. So I will better use the ones that can easily be minimized so that you get what I'm saying. So let me remove it. I will remove it, and I can't wait for it to minimize totally. I can't wait for it. So let me see this metformin. Let's look at the metformin with iron. But if you are the one working on this, you must wait. You must wait to see that everything is done, because you cannot use it until it's totally minimized. You can't use it until it's totally minimized. But for the sake of my time, I will proceed to, okay, better still, let me close it and reopen it. Let me reopen it, because you can't work on two molecules at the same time. You can't work on two molecules at the same time. Like if you are minimizing, you cannot minimize two different structures at the same time. So, but because of that one is taking a bit time, I just have to use something that will go faster for us. So on your own, you can start working on it. You can design, you can use metformin and design a nanoparticle of metformin with zinc, with iron, with cadmium, with nickel. Somebody may ask, I thought these metals are toxic. I thought they are toxic. So if we use these toxic metals, because they are heavy metals too, if we use these heavy metals to model a drug, and we are taking this drug in, won't it affect us? It will not. It will not, because the property it will exhibit as an individual metal will not be the same property it will exhibit as a nanoparticle. So this is my metformin. I just pasted the metformin. Very beautiful like me. This is the metformin. So let us minimize the energy of the metformin. I know this one will not take us much time because.
Sir.
Yes.
Are you saying that when because from all indication of whatever I'm saying here,
yes,
it is it's like you are doing that is a compilation of
yes,
metal with ligands.
yes.
Now, the fear of inorganic that is inorganic drugs is because of the side effects and what it will have with human.
Yes.
You understand? Does it mean that when we do it this way, we have already removed or extracted the hazardous nature of this inorganic?
Okay. All right. Now, let me answer the question. Let me use manganese, for instance. Let me use manganese. Manganese is a heavy metal.
Hello, can you hear me?
Yeah, I can hear you. I got your question. I got the question. I want to reply the question. Can you hear me? Hello? Can you hear me? Can you hear me clear? Oh. But I guess you will still hear me. Let me just continue.
We can, we can hear you.
Okay.
Go on.
Okay. The question is because
The question
the question is
I asked,
the question is, will nanocomplexes reduce the hazardous nature of these metals? That is the pure question. The answer is yes. Now, I want to cite one common heavy metal that we know. Manganese is a heavy metal. Manganese is toxic. When a pure manganese enters the body, it is very toxic to the body. But then, manganese is a cofactor for some enzymes. Manganese is a cofactor for some enzymes like arginase, carboxylase. Even in oxidation, manganese plays role in superoxide dismutase. There's this enzyme called superoxide dismutase. It is responsible for oxidation. So manganese is attached to that enzyme, but a pure manganese is toxic to the body. Let's look at iron. If iron enters your body, iron is toxic, but yet iron forms the hemoglobin. It forms the hem, the structure of the hem. That means every complex of these metals are not toxic. So I have to back up my explanation with some examples that are common to us. Whenever you have formed a complex of your metal, you don't expect them to be toxic, because at that complex nature, at that nano stage, they no longer possess the same characteristics with their ordinary metal state. They now possess the characteristics that are unique to that nano scale. That is the ideology. So when you form a metal complex like nanodrops, don't be afraid of the toxicity. But then, we are not saying that they will not be toxic. There is no compound without toxicity. Green chemistry is not 100%. Green chemistry is not 100%. But then we are now saying that it will have a less side effect. It will have a less side effect compared to when you are taking the pure metal, because there is no compound, there is no structure without a side effect. But our goal is, let us minimize the side effect. Just like how we are trained that error is inevitable in the lab, but as lab scientists, we now try our best to minimize the error, even though we know that it is inevitable in the lab, but we minimize the error. The same thing applies to, there is no compound without a side effect, but all our effort is to minimize or reduce the side effect. And nano compounds has less side effect. So you don't expect them to exhibit the same side effect with when you ingested the pure metal. That is all the whole idea. All right, so we have seen.
Excuse me,
All right.
I have a question.
Okay, go ahead.
You mentioned it earlier concerning the nano drugs. When you modeled your own, though the one you model is not exactly the same drug I model, but it seems like we had the same thing because it violated some of the rules that guide oral drug. So my question here now is, having known that making drugs nano makes it more active, where can it be applied? Since we have seen that it violated some of the rules that guide oral drugs, where exactly can it be applied? And then the activity which has been increased, how are we to test the activity to compare it with the normal drug that is not made nano?
Okay.
I don't know. Okay.
Yeah, I got the question. Now, I will answer it clearly. Now, I will answer it with a citation. I will answer it with a citation. Let me cite rifamycin. Rifamycin. I don't know if you know rifamycin.
Hello?
Can
Hello,
you hear
sir.
me? Can you hear
You
me?
are trying to explain something. Yes, I can hear you. You are trying to explain something about the question I asked you. Sorry, but network was hindering me from hearing you. But now I've changed my location to a better place. I believe I can hear or get network better. So
Okay.
maybe I would like you to repeat what you said.
Okay, let me just briefly say
Thank
it.
you.
What I said was, it will have, in summary, what I concluded was, it will have a lesser side effects compared to the pure state of the metal, because there is no compound, no structure, no molecule without a side effect. But our idea in doing chemistry is to reduce the side effects. So I will not tell you that these metal complexes we are modeling have zero side effect. It's a lie. But their side effect is very minimal compared to the pure metal states.
Does it mean that we can use it as a drug? Because there's the one I've already synthesized.
We already have nano
You
drugs.
gave me.
They're already there as drug. They are there
Okay.
as drug already.
Okay.
Yes,
There's
they
the
are
one
there.
I synthesized. Is to fight antimicrobial, that is bacteria and fungi, to reduce their, if I like, staphylococcus, what's it called, chylon, column, and what have you. And that means that because the thing has almost a replica of what you are doing here, it has 2:1. That is a 2 ligand to 1 metal. You understand? That means I've modeled it to nanoparticle.
Yes.
Okay.
Okay.
So what you mean is that
Go ahead.
I should advise that, yes, what you mean is that I should advise that it should be used to fight, because it actually inhibited the growth of some of these microorganisms.
Yes.
You understand? Like the
Let me
bacteria
cite-
and the fungi inhibited it.
Let me cite an example now. I think this my
Okay.
citation now we answer both Mr. Augustine's question. I don't know if you know this drug. If you know this cisplatin, there's a drug called cisplatin. Cisplatin.
Yes, I know cisplatin.
Good.
It's used in
Cisplatin has
fighting
platinum.
cancer.
It has platinum.
For fighting cancer.
Good. It has for anti-cancer. It has platinum. It's a nano drug. Cisplatin is a nano drug. It has a metal complex. We have I think we have statraplatin. It also have a platinum. It has platinum. Now, in as much as they have been made nano, they will exhibit higher properties. But then Chief Austin asked a question. The question is, when we subjected these nano properties, when we liken it to drug properties, we saw that it violated most or some, depending on the one you have modeled though. But the first one we did violated almost it evaluated all the drug likeness. Now, if I'm to work with that first one I modeled, number one, I'm not certain about the activity yet, but all what I know is that it will be more effective than the ordinary compound. Though in some cases I have seen where an ordinary compound was more effective than the nano. That is why we are bringing this idea so that we can build as much, we can model as much as possible and then test the activity. But then what if I had a nano compound that has a good activity, and let me borrow the idea of my boss. It has high antibacterial activity, but at the same time I subjected it to drug likeness and it failed all the drug likeness tests. Mr. Austin is asking, can it still be used as a drug? And why did it fail all the drug likeness tests? I thought Lipinski's rule of 5 said at least your molar weight should not be more than 500 grams. But now this nano drug, the molar weight is more than 500, so it has failed Lipinski's rule of 5. The answer is those models are not applicable for nanoparticles. Those models are applicable for ordinary particles, ordinary structures. Because those models, what those models are looking at is their structural makeup. What the model is actually interpreting is the structural makeup. This model does not interpret their particulate size. The model does not have business with their particulate size. What the model only sees to interpret is their composition, their structural makeup. So this model to him is seeing that the structural makeup of these compounds is not fit for a drug. But meanwhile, the particulate nature of that nanocomplex has already justified its nature to be as a drug. So that means, despite that the molar weight is now more than 500, and we are told that once the molar weight is more than 500, it will have a poor bioavailability and a poor human intestinal absorbability. But in this case, we have already reduced the particulate size. It can be readily absorbed by the body. Everything about the physical appearance, everything about the structural composition does not count again. What really now controls the behavior of that material is now the particulate size that has been reduced to nano. So that is the whole idea. So don't be discouraged when you see that your drug models disapproves the nanoparticle. That doesn't mean that it has failed as a drug. That is why I said earlier that we have to test their activity. We have to test their performance. It is now the activity that will justify if they are good or not. So you don't look at the composition as reported by these models.
Sir, when you mean molecular weight, we are talking of the molar mass.
Yeah, the molar mass or molar weight. Yes.
The molar weight of that, if it's the mass that will give you the extent, right?
Yes.
Now, so what you are trying to say is that if the compound or the compound has a molar weight that is higher than 500 mg grams, that it may or may not fit for being a drug or used as a drug.
Yes, according to drug likeness.
Okay, drug likeness.
Yes. But then let me help all of us. let me share a secret for you. Mr. Austin, are you with me?
Yes, I'm here.
Let me share a secret. If I want to model a nano drug, I don't go for structures that are heavy. I go for light structures. Like take a look at my screen now. I just modeled metformin. This is metformin, and I have looked at the formula weight, just 310. Despite that is a nanoparticle, but the weight is 310. So to still justify yourself, I will advise you to make every righteousness. If you want to create a nanoparticle, please look out for light structures that even when you compress it, the weight will still be around your acceptable range. But if you have a research in mind and that the structure is heavy, go ahead. If you have a research,
yes, I wanted to say something.
Yes.
I want to say something. Sorry,
Yeah.
like when you are doing it, you understand that you are trying to research. You try done anywhere before. You can get a cheap base and then get a lead, which I can compress with a metal, and then give me the nano particle, maybe used as a drug, maybe to fight antibacterial or to even fight cancer.
Yes.
You understand?
Yeah.
Now, if to go and use maybe a ligand with a lower molecular weight or weight that is is smaller or weight that is lower, it may or may not give me the exact what I want to do or try to have the breakthrough I want to
You want to get, yes.
make it happen.
That is true.
Yes. Yes.
That is true.
So
if you have
I don't know.
keen research, go ahead with it, because you are looking for novelty. Your idea is novelty, so you can still go ahead. It does not have any business. It will not affect you in anywhere. So if you look at this, my metformin now, I generated the smile code. I came to Swiss admin. You will see that.
Sir.
Yes.
Okay.
So you are seeing that my metformin ion complex is actually a good drug because it obeys Lipinski rule. It obeys Lipinski rule. So it all depends on, and if you look at this place, this is called boiled egg. Although I will still come to this part in chemoinformatics to explain about these things, but I just want to show you that as a beginner you can start developing nanoparticle with light structures, because you don't know whether they are effective or not until you test them. And that is the essence of we now using computational chemistry, because we will not waste our money going to the lab. After you synthesize, you start testing them. You will test them using your computational tools, like the idea our boss is sharing with us about antimicrobial. We can just model a lot of nanoparticles and conduct an in silico antibacterial studies on it and see which of them will be effective. So, but if I have a target molecule, whether it is large or not, go ahead with it. All what we are looking for is novel. What we are looking for is something that has not been done. So we have about 15 minutes. So let's finish our optimization, please. So this is
Sir.
yes.
Sir, there's a question I want to, yeah, sir, there's a question I want to ask. Like now, you mentioned ciplatin,
Yes.
right?
Yes.
Which is used in fighting cancer.
Cancer, good.
Which is, yeah, it is used in fighting cancer. But some studies have shown that since it's inorganic compound, that it has a damaging effect to an extent to some kidney and liver. I don't know, that's why more research they're trying to bring more of plant derived drugs that can even, if it's able to, that can be used to fight cancer. Even some people are doing some research work on venom of snake and scorpion.
Yes.
They said there's a research that was done that it actually killed the cancerous cell, but at the end of the day, the problem is that it starts damaging the living cell.
Okay.
You understand? Okay. So they were planning how to remove that particular constituent that is destroying the living cell, that is responsible for the destruction of the living cell, and then see how it works. But this a continuous hunt, research don't end until you make a breakthrough.
Okay, so
you understand?
I will advise when you model nanoparticle, look out for the toxicity as well. Yes, so when you model a nanoparticle, also look out for the toxicity properties. Let me show you a little bit, like this one we just model now. From this Swiss admin, you will know, look at this place now. This macrokinetics is giving you a little bit idea of the okay, here does not give information about if it's toxic or not. Let me show you. I'm now giving hint of next week class due to your idea, because it is advised when you are done modeling in a nanoparticle, check if it is toxic or not. It's breaking. Are you saying something? Oh, I was not hearing you clear.
You have not answered the last part of my question. I said, how can we test the reactivity of the nanoparticle and compared to the ordinary particle? Which model will we use? Can it be tested in silico or in vivo?
Yes, we'll test it in silico. You can test it in silico. In fact, do you know that you can do docking with nanoparticle? You can dock nanoparticles. You can dock. In fact, today I learned how to dock pure metals, like a metal against a target. How to dock a metal against a target. Because I received.
Sir, we can't see your screen.
Hey.
Did you share your screen?
Yes.
Oh, I cannot see the screen.
Okay, I'm coming back. Let me share the screen. Just that. Okay, you can see the screen, right? Can you see the screen?
Yes.
Now, due to the issue of okay, Austin, I have answered that you can do docking. You can use docking to test their activity and reactivity. You will use docking. So when we come to that, I will just show you a little bit how to dock nanoparticles. Although it's more advanced, it's a bit more advanced, but I'll introduce you guys to it, how to dot nanoparticles. Now, I was telling you that when you model a nanoparticle, please check for the toxicity. Check for toxicity. So this is another database. It's called ADMET. From this ADMET can tell you the toxicity of that your complex. So what I did here, what I did was just to kill in my smile code. Once I put the smile code, it will bring up this. Now, you will notice something. You notice that the full complex is not showing. The full complex is not showing. But something happened here. Ni minus. So this is just showing you that it's a complex, because I did not use the smile code of metformin. I use the smile code of my complex. So here you cannot check if it is toxic. Look at toxicity. So you can check the hedge blockers, DLI, MS toxicity, skin sensitization, carcinogenicity, eye corrosion, eye irritation, respiratory, human hepatotoxicity for liver, and nephrotoxicity for kidney, autotoxicity, all the rest. You can check all their toxic profiles, but I will really explain this more when I enter chemoinformatics. So let's just leave that area for chemoinformatics. So when you model,
Sir, this app you open, do you give it to us?
No. This one is a database, not a software. It's online.
Okay.
I will expose it to
Okay.
you.
Okay. Ahmed. Okay, I remember.
Yes,
Ahmed.
Our time is really saying that we have 7 minutes. So quickly, let me just finish up my business. We have not saved this man, no, although we know how to save it, but let's just do it together, because we have not saved this man. This is a iron 2 complex of metformin. So I'll just come to file. Let me just, the same thing we know, but let me just do it before we close. The same thing we know, SDF, you save it as iron 2 complex of metformin. We already know it, but I will just have to do it. So I have saved it. As iron 2 complex of metformin, but then I will still have to save again. This is iron 2 complex of metformin. Then we also know how to do again. Save again under Notepad. So save again under Notepad. So with this, we have actually modeled a 3D structure of your nanoparticle. You have actually modeled a 3D structure of your nanoparticle. Let me say this, please. Not all computational tools can recognize a nanoparticle because it's still new. So some of the old tools that we have built have not been able to recognize nanoparticle. Take for instance your Discovery Studio cannot interpret or recognize a nanoparticle. Let me try to open down my structure in Discovery Studio. You will see what it will tell me. So Discovery Studio does not, if I is not built to recognize nanoparticle. So always take note of that. It's still new, but I have some of the softwares that can recognize nanoparticle. That area is not within us. is not within the scope of this training. I reserved that area for February for the phase 2. But for this phase 1, I just have to explain how you can model a nanoparticle. Then we will do the docking. But a complete package of nanoparticle is advanced, is more advanced to us. It's just the one that is within your level. I will show you. Unless you want to now advance to specialize on nanoparticle, I'm available. I'm available if you want that area. I'm available.
You are highly available.
Yes, I'm highly available. So look at this man now. I don't think if it was able to recognize the zinc, because it does not recognize these nanoparticles. So let me keep it at white background. So now, if I want to do a visualization with this man, it will be so difficult for you to actually detect zinc. If I'm using BioVer Studio for visualization, it will be very difficult to detect the iron. Now, how will you know? If you look at this composition here, although I'm seeing Fe19, but if I want to subject this structure for visualization, it will not visualize it, probably after docking. It is limited. But what you can do is to use molar grow. There is this software called molar grow. In fact, let me just leave it for you. When we get to docking, I will explain more on this docking of nanoparticle. But I just want to show you the structure in BioVer Studio. But not all visualization can be performed by BioVer Studio. Most time, Chimera can do more for nanoparticle. PyMo cannot really visualize all nanoparticles. But I have successfully done justice to nanochemistry, the modeling and the optimization. I don't have any other area left. I don't think so. So I will give you assignments. I'm gonna try to I will drop the assignments. At least we now have partners, so it will be easier with our partners. It now depends if your partner is serious or not serious. Thank you so much for being around.
My partner. My partner, I don't know whether you don't want to join us.
Be like say they go check my partner. I don't know why they don't give me that and I can't go they give me person one.
Huh?
Is where?
My partner, I don't know, it's not responsive.
God will help you.
Even my own partner, I think my prospect, is he joining us?